In this video, we're going to talk about the second part of the Fundamental Theorem of Calculus. So we're going to start by stating this part of the theorem. And so, here's the Fundamental Theorem of Calculus, Part 2. And it says, if f is continuous on the closed interval a to b, then the integral from a to b of f of x dx equals capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, capital F prime of x is equal to little f of x. Okay. Now this theorem lets us takes definite integrals much easier, because we just have to find an antiderivative of our integrand and then plug values into it. And so, of the parts of the Fundamental Theorem of Calculus, this is probably the more used part, but it has a proof that involves the first part. And so we're going to prove this result and then do examples of using the second part of the fundamental theorem. So we're going to let little g of x be the integral from a to x of f of t dt. Okay, so we talked about functions like this last time. It's just giving us the area under the curve from a up to x. And then we know by part 1 of the Fundamental Theorem of Calculus that g prime of x equals little f of x. Okay, so that's what we proved last time. And so little g then is an antiderivative of f if we let capital F be any antiderivative of little f on the interval a to b, then capital F and g must differ by a constant. Okay, so we've talked about this before. Back when we were talking about antiderivatives, we talked about how if we have a function who has an antiderivative on an interval, that all of the antiderivatives differ by just a constant. That's why we had like the plus c at the end of our antiderivatives. Just say they differed by a constant. So what this tells us, this means that capital F of x must be equal to g of x plus some constant. For a constant, capital C, on the open interval a to b. Okay, so they only have to agree on the open interval, technically, because of where we're getting these from, since they're both coming from antiderivatives of f. However, we know capital F and g are both continuous. So if they agree on an open interval, they agree on the endpoints. Okay, so this is kind of just a technicality. We're basically saying that we actually have that capital F of x equals little g of x plus c on the closed interval a to b. And kind of a picture to see why this is true is what we have here, is we've got these two functions where we know everywhere from a to b, this is a, this is b, we know from everywhere from a to b that f of capital F of x equals little g of x plus c. We don't know if it's true at the endpoints, but we know the function's continuous. Both of them are continuous. And so as we approach an endpoint, we're forced to fill them in, and they have to fill in the same way because they're both continuous, so we can't jump to some other value. We're just approaching some value from the left and from the right, and it has to be the same for both of them because of continuity. And so because of that, they agree on the whole interval. And so that's going to be relevant in a second. Next, note that g of a is the integral from a to a of f of t dt. We talked about this last time. You get 0. If you're not going anywhere, then the area under the curve from a point to that same point is just 0. You don't have any width to speak of. And so now what we're going to do is we're going to look at capital F of b minus capital F of a. Remember, this is the right-hand side of the second part of the Fundamental Theorem of Calculus, and we're just going to kind of work to the right-hand side, the left-hand side, I mean. So we have capital F of b minus capital F of a. Well, this equals g of b plus c minus g of a plus c. Just plugging in the fact f of x equals g of x plus c. And then subtracting these, we get g of b minus g of a. But g of a, we just saw, was 0, so this is just g of b. And g of b, just writing it down, is the integral from a to b of f of t dt. That's literally what g of b means. And so what we found then is that the integral from a to b of f of t dt is in fact f of b minus f of a. And so that proves the second part of the Fundamental Theorem of Calculus. Now, the proof might not be particularly enlightening, but I think it's useful to know why it's true. Now, we're going to do some examples. And again, this is basically saying to evaluate a definite integral, we find an antiderivative of the integrand and then subtract its values at the endpoints. So let's look at some examples. So we want to find the integral from 1 to 3 of e to the x dx. Okay, well, we need an antiderivative of e to the x. Remember, capital F of x equals e to the x is an antiderivative. Okay, e to the x is its own derivative, so its antiderivative is itself as well. So that then means the integral from 1 to 3 of e to the x dx equals f of 3 minus f of 1 by what we just did, which is e cubed minus e. And so that then is our answer. E cubed minus e is the integral from 1 to 3 of e to the x. So that tells us the area under the curve from 1 to 3 of e to the x. Which that is way easier than doing all these limits of Riemann sums, which is why the second part of the Fundamental Theorem of Calculus is such a useful theorem. Now, there is a shorthand that we will use normally when using this theorem. So normally, we will write the integral from a to b of f of x dx equals f of capital F of x with a vertical line a to b, where this is an antiderivative of little f. So we'll take the antiderivative and write a vertical line from a to b, and then just plug in b minus a into the function. So that's just kind of a notational thing. It's pretty standard, and we're going to be using it in the next example. So hopefully you'll get an idea of how it works. Okay, so the next example, so we want to do the integral from 3 to 6 of 1 over x dx. So first we need an antiderivative of 1 over x. So we need a function whose derivative is 1 over x. Well, a candidate for this is the natural log of absolute value of x. Remember that we like this one better than just natural log of x because it has the same domain as 1 over x. Now, it doesn't matter here because we're going from 3 to 6, but we like the absolute values just because they have the same domain. And so the integral from 3 to 6 of 1 over x dx then is ln of the absolute value of x from 3 to 6. So So that's how we'd write down that notation I mentioned a second ago. And then we just plug things in. So we have the natural log of 6 minus the natural log of 3, which equals the natural log of 6 divided by 3 using log properties, which is the natural log of 2. And so the integral from 3 to 6 of 1 over x is just natural log of 2. So we were able to compute that quite quickly. Okay, next, we want to find the area under the parabola y equals x squared from 0 to 1. So we want to find the area under this parabola from 0 to 1. Well, what that's really saying is take the integral from 0 to 1 of x squared. Now, we have actually done this before using limits of Riemann sums. This is just to show you we can do it way faster. Well, what is an antiderivative of x squared? An antiderivative of it is 1/3 x cubed using the power rule. And we go from 0 to 1. So this is undoing the power rule. So this is going to be 1/3 times 1 cubed minus 1/3 times 0 cubed. And so we end up with 1/3. So the integral from 0 to 1 of x squared is 1/3, which then tells us that is the area under the parabola y equals x squared from 0 to 1. So again, graphically, what this looks like is we have this parabola, we go over to 1, and this area right here from 0 to 1 is 1/3. We have computed that before using Riemann sums, but this time we kind of got away with it a lot faster using the Fundamental Theorem of Calculus. Part 2. Okay, so let's look at 2 more examples. So next we want to evaluate the integral from 0 to 4 of 2 to the s ds. And I'm writing s just to make it clear that the letter we use doesn't matter. Now that is an s, not a 5. And so as long as this and this are the same, as long as our variable is the same as what we're taking the integral with respect to, we're fine. So now we need an antiderivative of 2 to the s. I'm doing this one mostly to remind you. The antiderivative of 2 to the s is 2 to the s divided by ln of 2. Okay, this is an easy one to forget. In general, the antiderivative of b to the x is b to the x divided by ln of b, and b is 2 in this case. So that tells us the integral from 0 to 4 of 2 to the s ds is equal to 2 to the s over ln of 2 from 0 to 4, which is going to be 2 to the 4 divided by ln of 2 minus 2 to the 0 divided by ln of 2, which is 16 over ln of 2 minus 1 over ln of 2. So we get 15 over ln of 2. And so that then is the value of our integral here. Okay. So now we want to look at one more slightly more complicated example. So now we want to evaluate the integral from -3 to 2 of f of x dx, where f of x equals 4 when x is less than or equal to 0, and 4 minus x squared when x is greater than 0. Okay, so remember for the Fundamental Theorem of Calculus, Part 2 to apply, we have to be continuous on the whole interval. So we'd have to be continuous from -3 to 2, in general from a to b. And so we need to check, is this function actually continuous on that whole interval? Now 4 is continuous, so it's continuous all the way to the left of 0. And 4 minus x squared is continuous, it's continuous all the way to the right of 0. So the only question is at 0. And so if we take the limit as x approaches 0 from the left of this function, well, if we approach from the left, the function is always equal to 4 from the left, so we just have the limit of 4, which is 4. And if we approach 0 from the right, this is the limit as x goes to 0 from the right of 4 minus x squared. We can plug that in to get 4 minus 0 squared, so we get 4. So they both are approaching 0 from both the left and the right. They both approach 4 from the left and the right as we go towards 0. And so because of that, this function is continuous at 0. So the Fundamental Theorem of Calculus Part 2 does apply here. And the way we're going to handle this is we're just going to split up the integral, basically. So we want to compute the integral from negative 3 to 2. But remember, we can split up integrals according to their bounds. So we're just going to go from negative 3 to 0 of the function, plus the integral from 0 to 2 of the function. And the reason why we're splitting at 0 is that's where it changes formulas. So for the entire first part, going all the way up from negative 3 up to 0, we have the same formula, namely 4. And then going from 0 to 2, we have the same formula, namely 4 minus x squared. And so we're just going along the interval where we don't change. So this becomes the integral from negative 3 to 0. Well, for negative 3 to 0, we're just at 4. And then from 0 to 2, the function is 4 minus x squared. So now we want to compute each of these. An antiderivative of 4 is 4x from negative 3 to 0, plus the antiderivative of 4 minus x squared is going to be 4x minus x cubed over 3 from 0 to 2. Okay, so we're just using antiderivatives that we already know. If you're a little rusty on that, going back to the antiderivative video might be helpful. Now plugging things in, this is going to give us 4 times 0 minus 4 times minus 3, plus we're going to have 8 minus 8 over 3 minus 0 minus 0, plugging things in. So here we're going to get 12 plus 8 minus 8 thirds. So we're going to get 20 minus 8 thirds. Just combining things. So this is 60 over 3 minus 8 over 3. So we get 52 over 3. And so the value of this integral is then 52 over 3. So we were able to compute the value of this integral. And so now, just as a note, just so you can see what to be aware of, say we wanted to look at something like the integral from negative 1 to 3 of 1 over x squared. Now, on the interval from negative 1 to 3, this function is not continuous. So there is an infinite discontinuity at x equals 0. So the fundamental theorem does not apply. Okay, so you have to have a function that's continuous on the entire interval. And so if I wanted to do from, say, 1 to 3 instead of negative 1 to 3, this would be totally fine. And we just take the antiderivative, so we get x to the negative 1 over negative 1 from 1 to 3, and plug things in, so we'd get negative 1/3 plus 1 over 1, so we just get 2/3. And so that would end up being totally fine. But we can't go from negative 1 to 3 because of the discontinuity at 0. So you have to make sure that you don't have a discontinuity in the middle of your range, or else the Fundamental Theorem of Calculus does not apply. Okay, one other thing to be aware of is I said that you can take any antiderivative. And so I'm going to give you an example just to make clear why. Notice in all of these I've been picking the antiderivative to be kind of the most basic one without the constant. In general, if you look at the integral from 1 to 2, or if from a to b, I guess I'll do a to b of little f of x. If I pick a different antiderivative, so I'm going to actually give a specific function here. So I'm going to use e to the x just because we've already talked about its antiderivative. So this two antiderivatives are all the antiderivatives like e to the x plus c. Okay, so every antiderivative is of this form. And so notice what happens when I do e to the b plus c for any constant minus e to the a plus c. So I've picked the same antiderivative. You have to pick the same one for both. Now when I actually combine them, the constants cancel out and I get just e to the b minus e to the a. And so that extra constant that would have been added on gets canceled. So say I was like looking at e to the x plus 5. That is an antiderivative. What happens when we do this is e to the b plus 5 minus e to the a plus 5. The 5's cancel out and we just get e to the b minus e to the a. And that'll happen no matter what antiderivative you pick. If you don't pick the constant to be 0, it's just going to cancel out. So we can always assume in the antiderivative we take when using the Fundamental Theorem of Calculus Part 2 that we're just taking the one with a constant of 0. Because if we didn't, we could have simplified it, and it wouldn't change the answer. So now let's mention the Fundamental Theorem of Calculus kind of in its completion, just so we have it all written down. So the Fundamental Theorem of Calculus says the following. If f is continuous on the closed interval a to b, then first the function g defined by g of x equals the integral from a to x of f of t dt for a less than equal to x less than equal to b is continuous on the closed interval a to b and differentiable on the open interval a to b with g prime of x equal to f of x. And then the second part says that the integral from a to b of f of x dx equals capital F of b minus capital F of a, where capital F is any antiderivative of little f. So this is the Fundamental Theorem of Calculus. And so the first part you can kind of interpret it as saying is if you take the integral of a continuous function and then differentiate it, you get back the end result. So taking the integral and then derivative, they undo each other. The second part says if you take the derivative and then the integral, they undo each other. Okay, and so, and to see that, just to make it clear on the second part, what I'm saying is if you do the integral from, say, a to x of f prime of t dt, this will equal f of x minus f of a. And so we're basically saying taking the derivative of the integral of a derivative undoes it up to a constant. And so that's where they aren't quite inverses, is this piece right here. So, in other words, the integral of a derivative is the original function up to a constant. Okay, so if you take the derivative of an integral, you just undo each other, but if you take the integral of a derivative, you might be off by a constant. Okay, and so they aren't quite inverses of each other, but they are extremely close to each other. Now, the second part of the Fundamental Theorem of Calculus is the part that gets used far more often, but it is good to know both parts